In previous episodes, we learned how to create pods, deployments, and services, but what happens when multiple teams and multiple environments share the same Kubernetes cluster? How do we separate development, QA, and production? And how do we manage different configurations for each environment? That's exactly what we're going to learn today using namespaces and config maps. Imagine your company has 3 environments: development, QA, production, all of them running inside the same Kubernetes cluster. Without isolation, resources become difficult to manage and naming conflicts can happen. Namespaces solve this problem by creating logical boundaries inside the cluster. A namespace is not another cluster. It is simply a way to organize and isolate resources. Think of it as separate rooms inside the same building. Each room can contain its own applications, services, and configurations. Development teams can work independently without affecting QA or production. Before creating our own environments, let's quickly look at the namespaces that already exist in every Kubernetes cluster. The first one is default. If you don't specify a namespace, Kubernetes will create resources here. Then we have kubesystem, which contains internal Kubernetes components such as DNS and control services. Kube public stores information that can be publicly accessible inside the cluster. And finally, Kube node lice, which Kubernetes uses internally to track node health and availability. In real projects, we usually leave these namespaces alone and create our own namespaces for applications and environments. Let's do that now. Let's start by looking at the namespaces that currently exist in our cluster. As expected, we can see the built-in namespaces we just discussed. Right now, we don't have any environments for our application, so let's create them. The first environment is development. This is where developers build new features, experiment, and make changes frequently. Next, we create the QA environment. QA stands for quality assurance. This is where teams validate functionality and perform testing before releasing software. Finally, we create production. This is the environment used by real users. Changes deployed here should already be tested and validated. Perfect. We now have 3 environments inside the same Kubernetes cluster. Notice that we didn't create 3 clusters. We simply created 3 isolated namespaces: development, QA, and production. Next, let's deploy applications inside each environment and see how Kubernetes keeps everything separated. In most companies, applications move through different stages. First, developers build features in development. Then, QA validates functionality and performs testing. Finally, the application is deployed into production, where real users access it. Namespaces are a perfect way to represent these environments inside Kubernetes. Now that our development namespace exists, let's deploy our application. For this example, we'll simulate a typical architecture with a front-end and a backend. The front-end will use an nginx container. The backend will use an Apache HTTP container. Notice that both deployments are being created inside the development namespace using the -ndev flag. If we list the deployments, we can see that both resources belong only to the development environment. Let's repeat the same process for QA. This is very common in real organizations. The application that developers use in development is promoted to QA for validation and testing. Even though we're using the same deployment names, Kubernetes allows this because they live in different namespaces. Finally, let's deploy the same application to production. Production is where real users interact with our system. In a real company, the code usually follows this path: development first, then QA, and finally production. Each environment has its own resources, but all of them can coexist inside the same Kubernetes cluster. This command is one of my favorites because it shows exactly why namespaces are useful. The -a flag means all namespaces. Notice that we now have front-end and back-end deployments in development, QA, and production. The names are identical. We have 3 front-ends and 3 back-ends. Yet Kubernetes has no conflict because each resource belongs to a different namespace. This is the foundation of environment isolation in Kubernetes. Applications are now separated, but in most real systems, applications also need their own databases. Let's add a database to each environment and make the separation even more obvious. One important rule in production systems is that environments should never share the same data. Developers need a safe place to experiment, QA needs test data, and production contains real user information. Let's simulate that separation by deploying a database into each namespace. First, let's create a PostgreSQL database in the development environment. This database would normally contain development data used by engineers while building new features. Any changes made here should not affect QA or production. Next, we create a separate database for QA. This environment is used for testing. Having an independent database allows testers to validate functionality without risking real data. Finally, we create the production database. This is where real application data would live. In a real company, this database would usually have stricter security, backups, and monitoring enabled. Let's look at everything we've deployed so far. Notice that each namespace now contains 3 components: a front end, a backend, and a database. Even though the deployment names are identical, Kubernetes keeps them completely separated because they belong to different namespaces. This diagram represents what we've built. Inside the same Kubernetes cluster, we have 3 independent environments: development, QA, and production. Each environment contains its own front end, back end, and database. This is one of the most common organizational patterns used in Kubernetes. Namespaces allow multiple environments to coexist safely inside a single cluster while maintaining clear separation between resources. So far, we've separated applications and databases, but environments usually need different configurations as well. For example, different API endpoints, feature flags, or application settings. Let's see how ConfigMaps help us manage those differences. So far, we've separated our applications using namespaces, but there's another challenge. Each environment usually needs different settings. Development might use test APIs, QA might use staging services, production uses the real infrastructure. We don't want to rebuild our application every time a configuration changes. That's exactly why config maps exist. A config map allows Kubernetes to store configuration separately from the application itself. The same application image can run in multiple environments while receiving different settings. Let's compare 2 approaches. On the left, configuration is hard-coded inside the container image. If the API URL changes, or if we need a different value for QA or production, we must rebuild the image and deploy again. That quickly becomes difficult to maintain. On the right, the configuration lives in Kubernetes. The application image remains exactly the same, only the configuration changes. This makes deployment simpler and much more flexible. Build once, deploy everywhere. So how does a config map actually work? First, we create a config map containing configuration values. Then, Kubernetes makes those values available to our application. Applications can consume config maps in 2 common ways: as environment variables or as files mounted inside the container. In both cases, the application receives its configuration at runtime. The important idea is that the configuration is no longer embedded inside the image. Enough theory. Let's create config maps for each environment. We'll create one for development, one for QA, and one for production. Then we'll see how Kubernetes keeps those configurations separated even when they share the same config map name. Before building the final demo, let's clean up the resources we created before. This way, we start from a clean cluster and the demo will be easier to follow. In Kubernetes, if we delete a namespace, Kubernetes also deletes the resources inside that namespace. So instead of deleting every pod or deployment one by one, we can remove the namespaces directly. Now let's organize our Kubernetes manifest like a real project. We'll create one folder for namespaces, one folder for workloads, and one folder for config maps. This makes the project easier to read, maintain, and reuse. First, we'll define our environments as Kubernetes namespaces. We'll create 3 namespaces: dev, QA, and prod. Development is where we build, QA is where we test, production is where real users would access the application. To create the resources, we use the kubectl apply command. Kubernetes will read every manifest inside the namespaces folder and create the corresponding resources in the cluster. This approach is one of the foundations of infrastructure as code. Instead of manually creating resources, we define them in YAML and let Kubernetes build them for us. Our environments already exist. The next step is deploying applications inside those environments. To keep things organized, I've already prepared the deployment manifests. Instead of writing everything from scratch during the video, we're going to copy the files into our workloads folder. Each file represents a complete environment containing a front end, a backend, and a database. This is very similar to how Kubernetes projects are managed in real teams, where manifests are usually stored in source control and reused across environments. If we open one of these files, we can see a standard Kubernetes deployment manifest. Notice the namespace field. This is what tells Kubernetes where these resources should be deployed. Even though the applications are identical, Kubernetes knows exactly which environment they belong to. Now let's deploy all of our applications. Kubernetes will read every manifest inside the workloads folder and create the corresponding resources. This includes the front-end, back-end, and database deployments for development, QA, and production. In just a few seconds, we'll have 3 complete environments running inside the same cluster. Let's verify the deployments. The -A flag tells Kubernetes to show resources from all namespaces. Notice that we now have front-end, back-end, and database deployments in development, QA, and production. The names are repeated across environments, but there are no conflicts because namespaces provide logical isolation. And here are the actual pods created by those deployments. Kubernetes automatically created the pods for each application. We can clearly see that every environment has its own front-end, back-end, and database running independently. This is one of the biggest advantages of namespaces. Multiple environments can safely coexist inside the same Kubernetes cluster. Now let's create a different config map for each environment. The config map will have the same name in every namespace, app-config, but the values will be different depending on the environment. Before creating the config maps, let's take a closer look at one of the files. Understanding the YAML is just as important as running the command. Once you understand one config map, the others will look very familiar. At the top, we have API version v1. This tells Kubernetes which API version should be used to create this resource. Next, we have kind config map. This tells Kubernetes what type of resource we want to create, in this case, a config map. Inside metadata, we define the resource identity. The name is app-config. This is how applications will reference the config map later. We also specify the namespace. Notice that this config map belongs to the development environment. The exact same name can exist in QA and production because each namespace is isolated. Finally, we have the data section. This is where the actual configuration lives. Here, we're storing 3 values: the environment name, the API endpoint, and the database host. These values are not hard-coded inside the application image. Instead, Kubernetes provides them at runtime. If we open the QA and production files, we'll notice something interesting. The config map name stays exactly the same, only the values change. This means the application can always look for a config map called app-config. The namespace determines which configuration it receives. Now that we understand the structure of the config map, let's create them inside Kubernetes and see how each environment gets its own configuration. Let's create a different config map for each environment. The config map will have the same name in every namespace, app-config, but the values will be different depending on the environment. Now we can see the full picture. 3 environments, same application structure, separate resources, separate configuration, same Kubernetes cluster. Let's inspect the development config map. Notice that the environment is set to development. We also have a development API endpoint and a development database host. These values are specific to the development environment. Now let's look at QA. The config map name is exactly the same, but the values are different. QA receives its own configuration without affecting development or production. And finally, production. Once again, same config map name. Different values. This is possible because Kubernetes isolates resources through namespaces. This is probably the most important takeaway from today's demo. We have 3 config maps with the exact same name, yet Kubernetes has no conflicts. The namespace determines which version of the configuration is used. Let's recap what we learned today. We use namespaces to create development, QA, and production environments inside the same Kubernetes cluster. Then we deployed a frontend, backend, and database into each environment while keeping everything isolated. We also use config maps to manage environment-specific configuration without changing the application itself. Remember, namespaces define where resources live. Config maps define how applications are configured, and together they help us build clean and organized Kubernetes environments. In the next episode, we'll learn how Kubernetes manages sensitive information using secrets.